I want to talk about probabilistic graphical models. Often abbreviated as PGM or even just GM for graphical models. And I want to start, well, by arguing why we need those in the first place. If we reason with certain quantities, we can resort to logic. So logic is all about reasoning with certitudes. And we have a couple of relations, like implies or is equivalent with, or negation. We have and, we have or, etc. Oh, Gewissheiten in German. So this is when things are either true or false, nothing in between, black or white. Whereas graphical models are all about, the shades of gray in between. Now to sure. Solve the following riddle. So he has a total of 2 white and 3 black feathers. So we have 2 white and 3 black feathers. And he offers to release them on condition that one of them is able to tell which feather is on his or her own head. I think those were guys, so is on his own head. Well, they will be. We don't want to think about the alternative, what happens to them otherwise. So these guys only know that at the outset he had 2 white and 3 black feathers. He puts a feather on each one of these hats, hiding, of course, the ones that he's taking away. And each one can only see the feathers on the guys' heads before him. Okay? And so now the question is asked, what color feather do you have on your head? Anybody knows this riddle? No? Maybe? Okay. So, well, they sit there for a while, and they're all very smart pirates, and after a few minutes, or maybe earlier than that, the first one says, I have a black feather on my head, and they're all freed. So what's the morale? Should, always hang out with clever guys. But how did he do it? Any suggestions? Now, it took me a while to figure out, so I'm going to, cut this a little bit short. So what are the possible configurations? We could have white, white, black. If this had been the case, then guy number 3 would have known that necessarily he must have a black feather, and he would have said so. But he didn't say anything. So guy number 3 says nothing. So we can rule out this configuration here. Now there are other configurations where the guys in front have 1 white feather each. And it doesn't really matter what the guy behind has. So this could be black or white. This could be black or white. Now, the second guy, hearing nothing from the first guy, would then know that these must be one of the 2 configurations, and he would see which color the guy in front has. So guy number 2 would have said black or white. But number 2 also says nothing. So this is guy number 1, 2, and 3. Number 2 also says nothing. So that guy number 1 rules out also this configuration. And now we're left with the following. We're left with a black here and either a white here or a black here and a black there, and here it doesn't really matter again what the third guy has. In any case, first guy will have a black feather. So one can speak up, and he now knows that he has a black feather. Okay, so this is something that you can do with logic by dealing just with zeros or ones. So the guy here sees exactly if these are white or black feathers. He can tell for sure, and hence draw his conclusions or not. And well, you can of course achieve lots of stuff with logic. It's not a course about logic, but a light treatment is given in this book, which I recommend to you. Actually, one of the authors here is a computer scientist, and he's written a nice textbook also on algorithms. So it's a fun book, I think. So that's what you can do with logic. But what if we don't have zeros or ones? This is where probability theory comes into play. So you could say that probability theory is all about reasoning with uncertainty. Or if you like a fancier word, then substitute reasoning by inference. Inference under or in the face of uncertainty. And inference is actually the technical term that's used in the field. And again, I want to give a motivating example. This is from a textbook by Jensen and Nielsen. The example is called stud farm. So a stud farm is a place where you breed horses, to win races or beauty shows or whatever. And we have the following situation. Each horse has a given probability of being a carrier of a rare disease or being entirely healthy. So if you remember genetics a little bit, those are the Mendelian laws. And when you have a recessive disease, then you can be a carrier. So one of your two chromosomes can be defect without, you showing any symptoms. It's only when two parents who are carriers, when they meet, then there are four possible outcomes, or three possible outcomes actually. The child can be entirely healthy, so it got two intact copies, or it can be a carrier, it means it got one bad copy, or it can be sick, it got two bad copies. Now here's the lineage tree of this horse, John, and those are just the prior probabilities. If each horse has a 1% chance of being carrier, 99% chance of being healthy, then these are the chances or the probabilities. So there's 99% probability that John will be healthy, and very, very small probability here has been truncated to just 2 digits, but there is a non-zero number there. There is some finite chance that John could be sick. Now, it so turns out that unfortunately John was born a sick horse. And now the question is, where did that come from? Who is to blame? And this is the lineage tree. And well, for somebody owning a stud farm, this is important because you don't want to use, the carrier again to breed more horses if you suspect that is a carrier. So here's the example, which I hope I can make a little bit smaller. Okay. And we can, for instance, look at all the probability tables here. How about John? You see there's some small non-zero chance of being sick. I could open these probability tables for everyone. And this tool, by the way, it's a belief and decision network tool. It's a nice open source tool to play around with. Now this is exactly the graph that you saw. And the a priori chances of K and L, which were apparently anonymous donors, So this is where they bought some semen. And Brian Cecily, they have the same a priori chance of being carriers or pure. And if we now make the finding that actually John is sick, who would you, suspect most to be a carrier among this generation of great-grandparents? Note that, we have just, in a healthy family, you would have 8 great-grandparents, and here there are just 5. Yeah, so I think I heard the right answer. Can you argue why? N. Yeah, why? Why is it N? She has more relations to her horses. Yeah, she's the great-grandmother of 3 out of the 4 grandparents. And indeed, there is a pretty big chance here. But there's also Brian, who is the father of 2 great-grandparents. So yes, I agree. And indeed, that comes out. But if you now would like to put numbers to this, this is what probability theory can help you with. So let's now make an observation here. I'm going to make the observation that actually John was sick. And you now see the probabilities updated everywhere. And indeed, Anne had a 2/3 chance of being a carrier. Brian had a 1/3 chance. And there is still some non-zero probability that any of the other horses was a carrier. Okay, so this is one particular instance of a problem that you can solve with probability theory, helping us in this example. Helping us in this example was the fact that the conditional probability tables or CPT for short of this system of discrete random variables, this was known from Mendelian genetics. And you've seen that the problem is conveniently expressed in terms of a graph. It's quite natural to draw this ancestral graph here. Now, what's special about probabilistic graphical models is that the joint probability density can be factored into functions that depend on only subsets of all random variables. So graphical models, in the language of Michael Jordan, are the result of the happy marriage, he doesn't say happy, between probability theory and graph theory. So a couple of comments on why these are interesting. They offer us a variety of ways of injecting prior knowledge. So we can inject prior knowledge through the structure of a graph, from which conditional independence assumptions follow, as I will show. Then secondly, we can inject prior knowledge through the factors. In this case here, the factors were conditional probability tables for directed graphical models, or energy functions for undirected graphical models. And we can inject evidence by making an observation. And these conditional independence assumptions or properties, they are all important, as we will see later, both in terms of computational savings that can be achieved, but also in the reliability with which you can estimate parameters, for example. So probabilistic graphical models encode how a joint probability density of multiple random variables, how it can be factorized into functions that depend on a subset of all the random variables only. Now, in addition, you get out compact and sometimes intuitive diagrammatic representations for your model. And it has become, in the last 15 years or so, an important unifying language for a number of approaches that were developed in machine learning, but also for methods that had been previously invented in other fields. So actually you have already seen a couple of graphical models in this course, or rather some of the models that we have discussed can be expressed in terms of a graphical model. And I'm showing you a few here. There's no need to copy down, but in linear discriminant analysis, for example, it's a generative model, and we were assuming or a way to generate samples in this model would be to assume that we are drawing a class membership Y, and I've shaded this node to say that this is an observed random variable, because in our training set we know the labels of our instances. And then given this class membership, I draw an observation X from a multivariate Gaussian, and I have two sets of parameters here. Actually, both Gaussians for the two classes would have the same covariance matrix, but they would have different locations. And there's also parameter pi that says how probable, what's the prior probability of one class versus the other. So that would be linear discriminant analysis. But if, on the other hand, in our training set we have only the observations without any class labels, then that would give you a Gaussian mixture model that we have also discussed. And you've seen that learning the parameters here was much harder because of these hidden variables, and we needed to somehow infer these hidden variables. Here's a model. I'm not sure what is its name. In a linear discriminant analysis, we just use a single Gaussian for each class. Here I've drawn a model where we have multiple Gaussians for each class, or where the mixing coefficients for a class density are a function of the class label. So in this generative model, we would draw a class label, then we would draw the index of one of the Gaussians, and this probability would depend on the class label. And finally, given this index of a Gaussian, we would draw a sample from that Gaussian. And I've drawn these funny boxes here around. They're called plates, hence also the title, plate notation. And this means that in our training set, this has been repeated n times, and these are independent. Now on the right hand side there is a model which looks almost the same, except that we have an inner box here. And this is another LDA, not linear discriminant analysis, but the latent Dirichlet allocation, where we have a generative model that is used in the analysis of text corpuses. So in this case, we assume that Z is a topic variable, and the topic is drawn from a mixture of topics, and then given the topic, a particular word is selected, and the difference between these models is that here one word can be associated with more than one topic, for example. So you can conveniently express different graphical models in here in a very, or different models in a very compact fashion. And this is one reason why they've become so popular. Now there are two big classes of graphical models, and then a few more specialized instances, but the two big classes are directed and undirected graphical models. And I will today only talk about the directed graphical models. They're also called Bayesian networks, or sometimes belief networks, or one says that such models are represented in terms of a directed acyclic graph, or DAG. Now, I could use the stud farm example, but it involves too many random variables and it becomes a bit tedious to write everything down, so I'm picking a smaller example now. Namely, an example from airport security. You know, you always have to go through these security checks. People want to know if you carry a bomb. And then, well, one way to diagnose if you carry one is to use a chromatograph. And I'm going to use some funny spelling here, because I need the C for something else. Or we could use an X-ray machine. And there may be confounding factors. For example, a serious confounding factor for plastic explosives is cheese. So it's not a good idea to walk through airport security with a kilogram of cheese taped together with duct tape and with wires hanging out, because people who do that are very suspicious. And I might have I think I have a screenshot somewhere from people who got arrested. So, you know, the guy carrying ice packs covered in duct tape, a wire coil wrapped around something that looked like an initiator, and 2 blocks of cheese, and so on. Yeah. So you don't want to do that, because you might be mistaken, or well, recognized as someone who's testing, you know, how well the security system is working, in order to find the weak spots and so on. So let's say this is the model that we have, and we now want to draw conclusions. For example, how likely is it that somebody is carrying a bomb if something suspicious is on the X-ray, and so on. Now first, how to factorize this graph, because this is what graphical models are all about, factorization. So we have a joint probability of all these 4 random variables. So we have a joint probability of B, C, K, and X. And in directed graphical models, each variable depends in a direct fashion only on its parents. So I can write that as the conditional probability of K given B times the probability of X given B and C and then we have a prior probability for B and C. Now this was for this particular model. In general, you can factorize any variables, random variables x1 through xn, which are connected by directed graphical model in terms of a product over all random variables, where random variable xi depends only on its parents, pa of xi. So this would be the set of all parents. And I don't need to include all the other random variables. It's conditionally independent of them. So I can glean a number of independencies here. For example, in this particular model, B is independent of C, or K is independent of X given B, or K is independent of C. And I will show why in a slide or two. So we have these independencies here, and this is where, well, part of the use of graphical models comes from. So if we had a fully connected graphical model, there would be no point in drawing it in the first place. There would be no structure that we could exploit. Here, however, it's really the missing arrows in such a graphical model. It is the sparseness of the graphical models that is going to be so helpful in the computations. So summarizing this statement, I say that the missing arrows are the important ones in a modeling sense. Now, in general, these rules of who is conditionally independent or independent in general, of whom else, these rules are given by a theorem revolving around d-separation, and I will show the relevant cases in a moment. Now, to really compute something, I still need to specify the parameters of this model. So the parameters in this case, where all random variables are discrete, are given by conditional probability tables. And I'm now making up these numbers. So I'm saying that the prior probability of a suitcase having a bomb is very small. The probability of somebody carrying some significant amount of cheese is perhaps that. Probably depends on, where the flight comes from and where it goes to. And then we have these probabilities. These are very important for the vendors or for the buyers of such instrumentation. So what is the probability of the chromatograph giving an alarm if we have no bomb or a bomb? So this is the bomb, this is the chromatograph, and let's say that there is, so these are the true negatives. I'm also making up these numbers. These are false positives. So there is no bomb, but the chromatograph saw one. I've given this a 1 per mil chance here. Then we have the false negatives. This is the very bad ones. So there was a bomb, but we did not see it on the chromatograph. I've given this 10 to the minus 4. And again, by the summation constraint, I must then have 0.9999. So by summation constraint, I mean that if I sum over all k's, I have to get 1. Okay, so we're still lacking the table for the X-ray device. Let's say that the probability of the X-ray raising the flag will be the following. We have a table. And then we have the two situations where, in truth, there is no bomb, or there is one. And then we still need the information about the cheese. So we could have no cheese or cheese. Okay, and here's the response from the X-ray. And let's say that the X-ray, it's nice because you don't need to physically touch the luggage and so on. But I've here assumed that it's not quite as reliable. So let's say starting with if indeed there is a bomb but no cheese, let's say this has an 80% chance of being seen. If there is a bomb and cheese, let's say this goes up to 90. And then I said that if there's only cheese, there's still a 70% chance of something going up, or a flag being raised. And this would be the false positive rate. So there's actually neither cheese nor bomb, and still in 5% of the cases, it somehow looks suspicious. Okay, so the model is now fully specified. So using these tables that we've just seen, using these tables, and by plotting this graph here, by having these numbers, I know everything there is to know in the framework of this model. So I've injected all my prior knowledge. Now both in this example and in particular in the stud farm example, the structure of the graph was given, so what is connected by arrows and in what order, and the tables were given. Here I made them up and pretended that they came from the manufacturer like this. In the stud farm example, those tables came from the Mendelian genetics. But sometimes we're not in such a lucky situation, so they were just given data and we need to infer the graphical model, and that is a much harder task. So that would be structure learning. So what usually we want to do, so tasks that we could have would be to just compute the probability of a certain observation, and for that we often need marginals. So that would be given the full model and given a query. Sorry, something's unreadable. I said. Oh yeah, it's reflection. It's a total reflection somehow between the light and the camera. I'm not using magic ink in the middle of the page. Okay. Bernhard is finding a reason to put in another optical component here. A pole filter, he just said. So. But sometimes we are given the model structure, but we need to learn these tables. So learn the parameters that would be given the structure and given training data. And sometimes we're left with the task to really learn the structure itself. That's the hardest of all. So this is given training data and also prior assumptions on the distribution of the random variables. And we have seen an example of that actually in the second week of this course, when we were discussing graphical Gaussian models and how to estimate sparse precision matrices. Whereas the Gaussian processes that we discussed last time, when we make a prediction, that would be about computing the marginals. Okay, so these are the typical tasks. Today we're going to make life easy. We will, for the most part of today, only talk about computing the marginals. Anyway, this is needed for learning the parameters, and we might talk about that in the context of HMMs later today. So thanks to their to these assumptions, to these independencies, graphical models make for a succinct representation. And this time I not only mean that in terms of how we draw it on paper, but actually how we can store it, how we can store all these numbers in a computer. And these conditional independencies allow for, depending on the model, huge computational savings. So to give you an idea of that, let's look at this particular model that we have here, the airport security. So let's consider the number of entries in the conditional probability tables. Well, and we need the priors also. So if we just use Bayes' theorem and nothing else, then I can write the joint probability of B, C, K, and X as the probability of X conditioned on B, C, and K times the probability of K given B and C times the probability of B given C times P of C. And we can count the number of entries here. So all of these variables here are binary, but graphical models in general are in no way restricted to binary random variables, but here we're using binary. So there are 4 binary random variables, which sounds like we have 2 to the 4 or 16 states, but actually we have this normalization constraint. This is why we have only half of it. So we have 1/2 times 16 for this one here. And then keeping track of the normalization, we have 8 over 2 for this one, and 4 over 2 for that one, and 2 over 2 numbers for that one here, which makes for a total of, so this is 8 and 4 is 12, 14, total of 15. And another way to arrive at that number is to say that, well, we have 4 random variables here, so there are a total of 2 to the 4 states minus 1, which we get from normalization, so that's a total of 15. Now if we use the graph, the graphical model that I've drawn, then this joint probability factorized as follows. X depends on B and C, but not on K, so I can omit K here. K depends only on B, but not on C. B and C are independent. And this is a total of 4 plus 2 plus 1 plus 1. So we have 8 entries here. So this gives us about a factor of 2. However, for bigger models that are sparse, this difference grows exponentially. So in particular, if you look at, let's say, sequential filtering methods as are used in tracking, if you represented the entire joint explicitly, you would have a huge number of entries. And using such models that roughly look like a chain, in such models you have only a linear growth of your parameters. So the difference here becomes more pronounced for larger graphs. Now, let's have a break, and after the break, I will show how these independencies here, how they can be jotted down for more general graphs. Yes, deseparation. It allows to study the basic motifs in Bayesian networks. So any Bayesian network you can decompose into the following 3 motifs. There is the converging situation, which we also have in our network. So we have both B and C pointing to X. And then the joint can be written as follows. And if, as long as we do not observe X, we know that B is conditionally independent of C. So we can see that by integrating out the third variable. So I'm marginalizing over X. So the summation only goes over the first term, and due to the normalization, we here have 1, and then we see that the joint probability of B and C factors into P of B times P of C. So it's already shown. But when we now start observing X, if we condition on X, we no longer have this independence. So I can write that as the probability of B and C and X, the joint divided by P of X. Well, and if you can insert these terms here, and in the bottom you need to integrate out B and C, but nothing cancels, and in the end you see that it's not the same as the probability of B given X times the probability of C given X. And of all configurations, this is the most interesting one, which explains away observations. So this has become a technical term. So in our particular case, the bomb has a very low prior probability, and X also, as we saw in the conditional probability table, responds to C. So if we do observe something in the X-ray, if we look or if we smell cheese in the suitcase or outside the suitcase, if we think that there is cheese in there, then this really lowers the probability that a bomb has explained the suspicious thing that we saw in the X-ray. We can also do this in numbers. Maybe I can start a second instance. Okay. .xml, okay. Let's try again. So let's use as many decimal places as there are. And actually I wrote that the prior probability should be 10 to the minus 6, but this program only allows up to 5 digits, so I've now made the prior probability of having a bomb 10 to the minus 5. And there you see our 3% chance of somebody carrying cheese, and given this rate of false positives, false negatives, etc., this evaluates to a 7% chance of you seeing something in the X-ray and 93% chance of the X-ray looking okay. Now, let's see what happens if we inject the observation that something was seen in the X-ray. So I'm making an observation. And note that before here, we had a 10 to the minus 5 chance of there being a bomb or a 3% chance of there being cheese. Now when I make this observation, each of them grow by a factor of 10 roughly. So we've gained one decimal place here, and we now have a 30% chance of having cheese in our suitcase. But we're still not sure. There's also a 2/3 chance that there was no cheese, and this was simply false positive by the X-ray. So now let's, in addition, insert the observation that yes, there was cheese, and let's look at what happens to our bomb probability. It goes back to practically the prior. It will be very slightly bigger than the prior, but not much. So in this case, the cheese has explained away the bomb. And you can try this out with numbers by yourself. Now the second interesting configuration are diverging arrows. Also in our model, we had the potential bomb being detected by the chromatograph and the X-ray. And the joint probability this time is given by probability of K given B times the probability of X given B times the prior probability of B. And it turns out that K is not independent of X. So if you insert this, whatever you do, you cannot transform it into P of K times P of X. But if, on the other hand, you condition on B, turns out that now you have independence. So the probability of K and X given B is that. Sorry, I need to divide by B. And now I can insert the prior here. I still need to divide, sorry, I meant I insert the joint, and I still need to divide by P of B. And now this cancels. And now indeed I find that the joint of K and X given B is the same as K given B times X given B, which is just the definition of conditional independence. So in this particular model, where the cheese is missing, as soon as we have learned that there is not a bomb, let's say, then the X-ray showing this or that picture does not tell us anything about what the chromatogram is going to say. I think I should have said spectrometer rather than chromatogram in the entire example. But well, I'll stick with it for now. And then finally, the third setting, one that was not in our model, is a serial configuration where we have, for example, X1, X2, and X3. Because this is not in our model, I have to make up an interpretation, and something that you typically model like this is some type of Markovian dynamics. So for example, a random walk or something like that, where the state X3 depends directly only on X2, which depends directly only on X1. So the joint factorizes like this. And in general, X1 is not independent of X3. So for example, if we have some correlation here and some correlation there, then by transitivity, we would also assume there to be correlation between the first and the third variable. So if I'm writing the joint and inserting the definition, I cannot reduce this to a product of the probabilities of X1 and X3. Whereas if I now condition on X2, then X1 and X3 turn out to be conditionally independent. So I'm inserting the same trick as before. I'm inserting the definition here. cannot cancel anything yet. However, I can rewrite this part as follows. This is the joint probability of x1 and x2, and I can factorize it the other way around. I can say this is probability of x1 given x2 times p of x2, which now cancels. And what's left is just a definition of conditional independence. And by studying motifs like this, you can make the following general statements. Namely that in a Bayesian network, some variables A and B who are not identical are deseparated if, now that's important that the following statement has for all paths, holds for all paths, that for all paths between A and B there must be an intermediate random variable C, such that one of the two conditions holds, either the connection is serial or diverging, and C is observed, or the connection involving C is converging, and neither C nor, and this is a frequent source of errors, any of its children are observed. So the statement here is that, sorry, I'm going to cover this for a moment. The statement here is that, so we here saw that B and C are no longer conditionally independent if X is observed. But this holds even if X has an observed child, because you can think of it as this, information propagating up to the parent X and then no longer blocking this path. And this statement here for all paths, that does not take into account direction. So it's this is true for, or you're looking at all paths, no matter whether you're running along or against the sense of the arrows. So you're ignoring the direction in your directed acyclic graph. All right. Now, these conditional independence assumptions, they are useful in inference. So they help you save work when you want to compute marginals, and the marginals you also need for learning the parameters in your model. I'm waiting for you to finish.